Okay, finally, let's look at these last couple of questions. Correct your entry. If this was confusing because you can't divide by 0, and then you worked it on the back, and then you put them right there, you're good. Like we just did. Okay. Now, totally different situation. What if we had a strong acid and a strong base? The pH at the equivalence point should be, if you remember from the last video, 7. Now just imagine that. How about HCl and NaOH, and they make water and a salt, sodium chloride. Notice this forward arrow. It's not an equilibrium. It's a strong acid. It's a strong base. They dissociate 100%. Every H bonds with the OH minus to make water. The sodium and the chlorides. And here's the real part. The real reason that the pH is 7 is because the sodium chloride aqueous does nothing. That's why the pH is 7. Sodium, the positive ion, is not a weak acid or a weak base. The chloride, the negative ion, is not a weak acid or a weak base. If you made something that's totally 100% soluble, then you are done and you are neutral. Okay, now, is the pH at the equivalence point of the titration of a weak acid with a strong base less or higher than 7? Again, we should know this from the last video and everything we've just done. So here's my weak acid. If I fully titrate it with my strong base, I shift this all the way to the right. I totally neutralize all of my acid, and these H pluses, they go off with the OH minuses, so they're gone. Look what I still have. A conjugate base. So, what do you think? Less than or higher than 7? When you're done titrating your weak acid, you have some conjugate base there, even if it's very weak, like the acetate ion has a very low Kb, something times 10 to the negative 10, but it will still be enough to make it just a little bit higher than 7, just a little bit basic. Okay, I hope your homework went well, and that the Henderson-Hasselbalch equation and shifting a weak acid equilibrium is a little bit more clear.